Like the sample variance, the average in equation 3.24 is computed by dividing n minus 1 instead of n. Here too, this difference stems from using big X bar and big Y bar to estimate the respective population means. When n is large, it makes little difference whether division is by n or n minus 1. The sample correlation coefficient or sample correlation denoted R sub big X big Y and is the ratio of the sample covariance to the sample standard deviations. R sub big X big Y equals S sub big X big Y over S sub big X S sub big Y. Equation 3.25. The sample correlation measures the strength of the linear association between big X and big Y in a sample of n observations. Like the population correlation, the sample correlation is unit-free and lies between -1 and 1. The absolute value of R sub big X big Y is less than or equal to 1. The sample correlation equals 1 if big X sub I equals big Y sub I for all I and equals -1 if big X sub I equals negative big Y sub I for all I. More generally, the correlation is plus or minus 1 if the scatter plot is a straight line. If the line slopes upward, then there is a positive relationship between X and Y, and the correlation is 1. If the line slopes down, then there is a negative relationship, and the correlation is -1. The closer the scatter plot is to a straight line, the closer the correlation is to plus or minus 1. A high correlation coefficient does not necessarily mean that the line has a steep slope. Rather, it means that the points in the scatter plot fall very close to a straight line. Consistency of the sample variance and correlation. Like the sample variance, the sample covariance is consistent. That is, S sub big X big Y converges to sigma sub big X big Y or moves towards big X sub Y, sigma sub big X big Y. Restarting, that is S sub big X big Y moves towards sigma sub big X big Y through P 3.26. In other words, in large samples, the sample covariance is close to the population covariance with high probability. The proof of the result in equation 3.6 under the assumption that open big X sub I and big Y sub I close are independently and identically distributed, and that big X sub I and big Y sub I have finite fourth moments is similar to the proof in appendix 3.3 that the sample covariance is consistent and is left as an exercise, open exercise 3.20, close. Because the sample variance and sample covariance are consistent, the sample correlation coefficient is consistent. That is, R sub big X big Y moves towards the correlation of big X sub I and big Y sub I with high probability as sample size get large, presumably.